But like, yeah. It's a bit hard to see. Yeah.
All right. Let's see. So it seems that people stopped trickling in. Welcome to our third session of the day. So today we have as our invited speaker Agnes Ferte from Slack. She will talk to us about challenges and opportunities for testing cosmology in the Roman era. And yeah, a pleasure to have you here, and take it away.
Thank you, and thank you so much for the invitation and the organization of this conference, and congrats for a beautiful telescope. So I'm Agnes Ferte. I work on the Rubin Observatory at Slack, and actually the background here is one of the first look images from the Rubin Observatory, which I hope you already have been exploring and zooming in and out those beautiful images. So I'm excited to talk about cosmological inference and testing cosmology and what it means to do it in the new era of cosmological surveys. But to start with, let's take a step back. We have a great, nice model of the universe, the lambda CDM model, where density perturbation that got created during cosmic inflation got imprinted on the cosmic microwave background, and later on collapsed to form the large-scale structures of the universe today. A very nice model that explains the story of the universe, but as we have seen multiple times today, cracks are widening. So one of the big questions that's appearing is dark energy really a cosmological constant, lambda? Because as we see from bionic acoustic oscillation, from DESI, or from DES, as shown here, in combination with supernovae, we see a deviation from lambda CDM and a preference for a dark energy that's varying with time. And in addition to that kind of crack, there are also big open questions like, is general relativity valid on such cosmic scales? What is dark matter? That is actually most of the matter in the universe. What is the mass of the neutrinos? So I think we should be especially excited to be working in cosmology where we have such opportunity for discovering given those big questions and cracks in the lambda CDM model. So as a community, we're kind of going after several things. So first, we are doing high precision measurements of the cosmological parameters across probes and experiments in lambda CDM. And in doing so, we're seeing several tensions in S8, for instance, between the CMB and galaxy surveys. So S8, which corresponds to the amplitude of clustering, but also in the Hubble parameter H0 between CMB and Cepheids and others. But there is also a tension in the matter energy density, omega m, between CMB and supernovae. And it's actually what is driving this evidence for a dynamical dark energy. So there are several tensions, but we spend millions of dollars to develop those big experiments. Like, we are also going after the big question, like what is beyond lambda CDM? So focusing on testing the test of gravity and testing the growth of large-scale structures, there are different ways that we can do it. So first of all, you can directly look at signature from any deviation from lambda CDM. directly in the growth of structures. So for instance, you can measure sigma 8 at different redshift bin, like we had done in DES, or you can directly test the growth of structures with this parameter gamma that is supposed to be 0.55 in lambda CDM. And in fact, this paper is showing deviation from lambda CDM in this parameterization. Then in kind of like a middle way of modeling deviation from lambda CDM in terms of growth of structure, you can consider general parameterization. I'm personally a big fan of this sigma mu parameterization, so I'm gonna use it as an example in this talk, and I'm gonna quickly explain what it is. So it's a way to parameterize deviation in the gravitational potential. On the one hand, the gravitational potential that drives the lensing, so the potential that impacts the photons. And on the other hand, we have this parameter mu that parameterizes the gravitational potential that impacts matter, so that impacts the growth, like how galaxies cluster. So this is a very powerful way to probe, to test gravity through lensing and through galaxy distribution. And there are also alternative ways of doing so using Horndeski, effective field theory, etc. And then kind of like on the other end, you can also just pick your favorite modified gravity theory or dark matter model. And this is an example for one modified gravity theory, and you constrain parameters given your data. So to kind of like answer those big questions, the community spend a lot of time building those massive surveys like Euclid and the Rubin telescope from space, the Rubin Observatory from the ground in Chile, the spectroscopic DESI survey that's already been going on, and the Simons Observatory, the CMB experiment. In terms of cosmology from those big optical surveys like the Rubin Observatory, there are several types of probes that we can use to test cosmology and the standard model. So from mapping, from imaging galaxies over a large part of the sky, we can get kind of like two types of information. Like we heard today, we can probe distances in the expanding universe. That's difficult to do, but thankfully we have kind of standard rulers or standard candles like bionic acoustic oscillation and supernovae to kind of probe how the universe is expanding, and so probe dark energy, for instance. But then we can also use galaxies to probe how the large-scale structures of matter in the universe are growing with time, and that depends directly on dark energy and gravity. And I'm especially going to focus on using galaxies using weak lensing and clustering of galaxies to probe the growth of large-scale structures. Because indeed, we can use galaxies in two different ways. First of all, as a tracer directly of those large-scale structures, because galaxies form where there is dark matter. So in that case, they trace dark matter structures directly, and we call those galaxies lens galaxies. We can also use the galaxies as background light. So those galaxies, those source galaxies, will be affected, the light coming from those galaxies will be impacted by the gravitational potential created by the large-scale structures. So as a result, they will be weakly lensed. They will have a coherent distortion that we can then use to kind of reconstruct the intervening matter between us and those galaxies. And because this effect is very small, and it adds to the intrinsic shape of galaxies, we need thousands or millions of galaxies, which is why we developed such large galaxy surveys. So when we don't have access to spectra, like for the Rubin Observatory, for instance, we have to estimate the redshift of galaxies from those big broad bands. So in this case, we distribute galaxies in redshift bin, and then to pick out the weak lensing signal, we correlate the shape of galaxies as a function of their distance on the sky. So that's the 2-point correlation function, and you see the different boxes. That's for the different redshift bin that we're using. So in the end, we can do this exercise with, on one hand, correlating the shape of galaxies. So in that way, we probe directly the intervening matter structure. We are directly sensitive to the matter power spectrum. On the other hand, we can correlate the position of galaxies, so using galaxies as tracers. So in this way, we probe matter power spectrum, but with a bias square. And then we can correlate the shape of galaxies around lens galaxies. So now we have 1 factor of the bias. And we can combine all of those correlation functions into what we call 3x2 points. And that's especially sensitive to the growth of structure, to sigma 8, to omega m, and tests of gravity. And here I'm showing forecasts for Roman. So this is from Tim's paper on this sigma mu model I was telling you about. So, and this is a forecast that I've made for LSST, which is probably way more optimistic. As you can see, the order of magnitude is much different. But for me, that's a huge motivation, you know, that we have a gain of 1 order of magnitude between today and what we expect with those new surveys. So to go from those nice 3x2 point measurements here and go to the cosmology, we generally assume a Gaussian likelihood where we compare our model of, for instance, 3x2 point in this case. We compare to the data, taking into account the covariance matrix. So in general, we use an analytical description of the covariance matrix, or we can use also the data. And this is also a huge challenge that's coming, that's going to take a lot of time as well in the new era. But I'm going to talk mostly about the modeling parts, where now we need to do theoretical prediction of those 3x2 points. And this depends on many things, but one of the main underlying ingredients is the matter power spectrum, which I'm showing a GIF here of how it changes with time. Okay. So that's this cosmological analysis. We have done several of them within the dark energy survey. So DES is a precursor survey to this new generation of experiments. It's a 6-year photometric survey of the southern sky using DCAM at the Blanco 4-meter in Chile. So it mapped 10% of the sky in 5 optical bands from 2013 and 2019. And so we released several cosmology from the different years of observation. And at this moment, we are working on the very final analysis. And Martin and Massa, who are here, are going to talk more about this analysis. But I'm going to use it as an example of the challenges that we're facing. Like that's, real life data analysis challenges that we'll have to fix for Roman, Rubin, Euclid, etc. So one of the things, this is showing constraints on this sigma naught parameter. So how the lensing potential, testing the lensing potential, how it compares to GR, which is corresponds to sigma naught of 0. And you see this is kind of like a history of the measurement of sigma naught using 3x2 cosmic shears and 3x2 points, in addition to CMB and in addition to redshift space distortion to constrain the mu parameter. And what I want you to see here is that those experiments are getting better and better, right? But the error bars are not getting that much better. And this is my optimistic forecast that we should aim at achieving. And so why are those error bars stagnating? So the real limitation here is in the uncertainties of the modeling of the 3x2 points. So here I'm showing an example of the clustering of galaxies. And in here, there are many things that intervene in the model of this correlation function. So first of all, the matter power spectrum on small scales has a nonlinear evolution that we need to describe. Then the matter distribution on small scales is impacted by the feedback of AGN or supernovae. Then we also need to describe how galaxies are tracing the underlying large-scale structure. So we need to model that as well. And we also need to model how galaxies are intrinsically aligned because of the gravitational environment. So this is the intrinsic element of galaxies. So we do have models for these different kind of like effects, astrophysical effects, but they are uncertain. There is a lot of uncertainties in this model. So that was part of our effort in the modeling team in the year 6, which was to say to what scale do we trust those models? So as you can see, this is a large team because it's actually a very difficult task, so be prepared. So I've been co-leading this team with David Sanchez-Cid and Jonathan Blazek, who is here this week, and this wonderful team, including Massa, Martin, Alex, who are here this week as well. So as a result, we thought that we wouldn't trust our model on those small scales, and we ended up removing 34% of the possible data points because of the uncertainty of this modeling. And in sigma mu, in the analysis of the 3 years of observation from the ES, we removed more than 50% of the data points, and that's really a huge limitation. So that's one of the challenges. Another challenge that I want to convey is that we have a large parameter space due to modeling those different ingredients to the 3x2 points modeling. So first we have the cosmological parameters. Then we also need to model the data uncertainty, like our estimation of the photometric redshift, the magnification, etc. And we also need to model the different effects I was just describing before. So as a result, in the year 6, we are varying 50 parameters in our cosmological inference. And this will only grow for the new surveys because there will be more complicated model, more redshift bins, and you need like 1 parameter per redshift bin, etc. And as you also get more precise data, you need to model your data better as well. So that makes it very challenging. And especially because every step of that cosmological inference, where we're like sampling the likelihood and looking for the best fits, this is a very intensive step. So for our effort that took 2 million CPU hours, and also something that we've been experiencing in the 3x2 point analysis in the ES, is that new samplers that come on the markets are fail quite often for our case because we have such a difficult parameter space and likelihood space. So that's one challenge. Another big challenge that we have been facing is, again, because of this large parameter space, is that when assuming you know exactly the underlying cosmology, doing your cosmological inference, you will not necessarily recover the cosmology, the input cosmology. So this is an example here showing how I know this S8 from my input data vector has this value, but when I do my cosmological inference, I get this bias in my estimate of S8. So that's what we call projection effects. There are many projection effects in cosmology, but this is what we mean in general here. It's this bias, this kind of like intrinsic bias on the parameter estimation. And that's in general because there are some parameters that are weakly constrained. And so as a result, some of the other parameters will be impacted by this sensitivity. And this is also another example is that my forecast on sigma mu, like my simulated data vector, has 0 deviation from GR. It's just a lambda CDM model. But if I do my cosmological inference, I get a sigma naught of 0.5. So I would have like detected a deviation from GR. So that's a problem. So we have to do more reliable estimates of the posterior of the values of the parameters, the preferred values of the parameters, better tension metrics, and also determine robust parameter combinations. Another big problem as well is that if you want to use more data or more precise data, you also need a more complex model. And so that means in general that you need to add more parameters to describe, to take into account in your model. And this is an example in our analysis in DES, that when we actually use more scales in the WCDM model, we actually are, because we have a more complicated model of the galaxy bias, we are diluting some of the constraining power, and we get slightly less constraining power when using more scales here in red. So that is something that we will also have to take care of as well. An additional challenge is that, again, we are also going after the big questions, you know, like what is dark energy? Is GR valid on cosmological scales? What is dark matter? And in all those cases, there are many, many possible models and theories, and it's already complicated enough to do in lambda CDM. I don't think we want to do it for all those cases. So this is also a real challenge. So now I'm going to try to lighten up the mood a bit, talking about opportunities in the Roman era to tackle those challenges. And the first thing I want to talk about are the synergies between all those different new experiments. Like Roman is coming in with other surveys, and the synergy between them is great. And there will be several talks this week to learn more about it. So as a Rubin scientist, I want to talk a bit more precisely about the Rubin Observatory. So it's a US-Chile observatory on Cerro Pachón, so the mountain just next to where the dark energy survey was done. And it's going to perform the legacy survey of space and time, the LSST, a wide, fast, deep survey of the sky. And the power of the Rubin Observatory is that it has a massive field of view with 3.5 degree diameter field of view. And that's thanks to the 8-meter Simony telescope that's shown here. It's really compact. And the LSST cam, the largest camera ever built. And so this is here, it was built at SLAC. So this is a picture I got to take there. And it was sent to Chile earlier this year. And now we are taking data with the telescope and the camera. So we are commissioning, and the survey is set to start later this year and will go on for 10 years. So I hope you heard about the first look data as well. So this is the first time we released publicly some of the images from the Rubin Observatory. And because there is so much data, we can't show it like on a screen, like you would need 500 4K monitors to see it all in its full resolution. But you can go to this app to explore those images yourself and zoom in, go to your favorite galaxies and really enjoy those news data. And importantly, a few weeks ago, we released data preview 1. So this is the first release of real Rubin data from the commissioning camera. So from the campaign, observing campaign from last year with a small version of LSST cam. And that's available to data rights holders. Another big opportunity that we will hear way more about this week is that we can do direct measurements of the different effects, the different astrophysical effects that enter the 3x2 point modeling. So for instance, for baryonic feedback, we can directly probe the amplitude of the baryonic feedback through the CMB SE effect, through X-ray, fast radio burst, etc. And for intrinsic alignment, we can also use the combined spectroscopic and photometric surveys to directly measure its amplitude and how it changes with different type of population of galaxies. And finally, for the galaxy bias, we can also exploit the constraints from lensing versus from probing galaxies directly. So again, a lot of talks are coming this week to learn more about all of this. And finally, here I want to highlight again what was explained in the first session, that simulations are really like a necessary ground to be able to develop all the tools and new approaches that we need to go beyond what we're doing right now. So one thing that is that one of the opportunities is using new tools to first emulate the power spectrum or your data to accelerate this type of cosmological inference. So for instance, in the DESI analysis, we used at some point the Euclid power spectrum emulator, and that reduced the runtime by 2. But then again, you need to like validate those emulators that you're using because sometimes they fail. And there are also new samplers that are taking advantage of machine learning, like neural networks that are also coming out, and that will be also extremely powerful to accelerate that step. Also, there is a lot more information beyond the 2-point correlation function, and that as well we heard about earlier today, either in the bispectrum or at the level of the map. And again, we can use machine learning to go from directly from those maps to inferring cosmology and gravity, for instance. I also just wanted to highlight as well that we had proposed, like regarding the challenge of how to test such a wide variety of models. Well, we suggested to use unsupervised learning to characterize how different models are impacting our observables. And as an example, I'm not going to explain too much about it, but just an example is that we showed that the dynamical dark energy has a completely different signature on cosmic shear than modified gravity models. So when we are doing modified gravity, we also kind of have to do dark energy at the same time as well, because that gives us different information. So finally, there are a lot of challenges, and the different collaboration will have to kind of like seize those challenges and solve them. But we are really kind of like in the best place to solve those challenges, thanks to synergies between experiments and the rise of new tools. Thank you.
We have time for one quick question. Questions online?
There's a question here.
Yeah, so how do you see Roman impacting the most, for example, in Rubin and cosmology?
Yes, so again, there are people in the room who can talk more about the synergies between the two, but basically, so first of all, one of the particularities of Rubin, for instance, is that it's a deep survey, and it has 6 optical bands, and that makes it complementary to Euclid, for instance, and to Roman. So they are both from space, so they have the resolution that will help Rubin, but our like 6 optical bands will also help Roman and Euclid. So as a result, we'll get better Wick lensing, so 3x2 point measurements. So we'll get better cosmological parameter test. And also I'm very excited about this sigma naught measurements that will get much better as well with those experiments.
Let's thank Agnes again. So next we have Yu-Xiu Huang from University of Arizona.
Hello, everyone. I'm Yu-Xiu Huang. I'm a grad student at the University of Arizona. So first, thank you for the opportunity for me to present here. So I'm going to talk about a 3D cross 2D. Can I play this? Yeah. I'm going to talk about 3D cross 2D, combining spectroscopy and image measurement with Roman. More specifically, I want to focus on the multiple analysis centered around the kinematic lensing. So before I dive into what exactly is kinematic lensing, let me first introduce the amazing team I'm working with, the Roman WFS kinematic lensing team. So within this team, we have developed the core idea of the kinematic lensing, developing the measurement pipeline. Also, we have recently done a pilot measurement from the real data. So here I put the archive number for all the published papers down below here. And if you are interested to know, please do check out. Okay, so back to the topic. What exactly is the kinematic lensing? So kinematic lensing is basically a new weak lensing technique like this aimed to beat down the shape noise. So in traditional weak lensing, we cannot simply tell the difference from the lensing effect and the galaxy's intrinsic shape. So from the below, I show two images. So on the top is this galaxy is face on but lensed in the bottom. There is another this galaxy is unlensed, but this is inclined to our light side. So in the image, you cannot tell the difference between these two images, right? So that is the so-called shape shear degeneracy in the weak lensing. And this degeneracy leads to a statistical uncertainty in the weak lensing called shape noise. So to extract a clear signal of the weak lensing analysis, we usually need to include as many galaxies as possible. That means we usually have to include faint galaxy where the shape and redshift estimation is very challenging. However, there's a different story here. Like if we put two slits onto these two galaxies and measure their spectrum, because one of this is slightly inclined to us, we can measure the rotation curve of light, and we cannot measure anything of the other galaxy. So in the spectrum, you can clearly see a difference between these two galaxies. So this is the core idea of the kinematic lensing. It's that by including the galaxy kinematic information, we can break the shape and shear degeneracy. And of course, in practice, we doesn't just put two slits onto a galaxy and tell the difference. We actually do a full modeling between image and spectrum to measure the shear on a per galaxy basis. And by doing so, we found that we can reduce the shape noise by an order smaller than the traditional weak lensing. Yeah, and there are more complicated stuff that I don't have the time to cover. So please see Jiatran's talk tomorrow to learn more about the kinematic lensing. So back in 2022, our team have done, Jiatran has done a KL forecast for Roman. So using the survey configuration and length, he concluded that the KL can achieve about 3 times more constraining power in the WCDN. So now in 2022, this forecast is a bit outdated. With our newest high latitude wide area survey in a median tier, we are going to have a 2,400 square degree of sky coverage. And we are going to have around 19 million galaxies with spectrum plus image. So this will be our new KL dataset. And with this joined 3D and 2D dataset, we are going to ask one question. What kind of multiple KL analysis we can do other than just doing KL? So this is tied back to the big topic in my talk. So our goal is trying to explore anything that we can do with this 3D cross 2D dataset. So first, like KL is definitely one of the 3D cross 2D example analysis where we can give very good constraint on cosmological parameter, especially omega and sigma 8. With the same data set, because we have spectrum, we can actually do a clustering, which with a clustering, you have a good constraint on F and sigma 8. So combine this together, of course, you can break the degeneracy between F and sigma 8 to directly testing the GR and the dark energy model. So combining the clustering and lensing is not a new thing. It has been studied for years. So what's new here? So in the light of the recent DESI results, like testing redshift evolution of dark energy is become more and more important. So with the kinematic lensing, we will be able to have a final tomographic beaming, meaning that we can measure a much localized ratio evolution of a growth rate compared to the weak lensing. So this will be very helpful if you want to detecting any transition in your dark energy model, or to testing any dark energy model that returns non-smoothing evolving features. So our first step toward full 3D cross 2D is a KL 3 cross 2 forecast, and the forecast done within the high latitude survey median tier. So we update our KL sample using the Cosmos catalog. The new survey strategy gives us slightly lower number density compared to our previous strategy. And on the right, I show there's a ratio distribution just for reference between the new and the old survey difference. And we do a lot of work in the COCOA and cosmology, which this is a very fast likelihood pipeline anyone can use, and I've put a link here. And also one of the highlights within this COCOA is that we have been developing a neural network emulator for specifically for Roman 3 cross 2 for accurate and fast likelihood analysis. So for this part, do check out Haley's posters. Okay. So first of all, we need to see how the change of the survey configuration impact our KL performance. So on the right, I compare the new and the old KL forecast. And you can see that there's not much significant integration in the omega m and sigma 8, which is a good news for us. But we do see, like, if we do this forecast in a WCDN scheme, we do see some integration in for the new survey. So we still suffer from the degrading of the number density here. And one step further is we do perform a 3 cross 2 analysis. And again, I show the contour on the right. You will see like here, the KL actually dominate the most constraining power in the 3 cross 2, compared like 2 cross 2 is kind of not contributing much in our 3 cross 2 analysis. That's because lots of information has been lost during the projection from 3D into 2D. So that leads to our next step is we want to extend into the narrow tomographic beaming of the projected power spectrum to fully capture the RSD information. So we are currently running a test for static tomographic beams. That means the limbar approximation will no longer work here. We need to switch into a non-limbar calculation. And this is why like emulate become very important here, because non-limbar calculation is actually very time consuming. So we definitely need help from a fast emulator. Another approach we are taking right now is we are adding a 3D meta power spectrum into our database, such that we can fully capture the 3D information. To sum up, so I hope I have convinced you that KL is a very powerful new recurrencing technique, and with the high latitude wide area survey will be a perfect data set for KL and the KL multi-probe. We have explored the 3 cross 2 KL 3 cross 2 as our first step toward the full 3D cross 3D, and we have been showing that if with the current set out the KL is the dominant constraining power in the 3 cross 2. And so our next step is trying to recover all the 3D information lost during the projection. And because you have seen that we have been showing that the decreasing of number density actually hits us still quite a few. So we're interested in collaborating with people that can basically get more galaxy out of the Grissom sample to increase our number density. So please come talk to us if you have any idea that can increase our sample size. And thank you for everyone.
Thank you so much. Any questions?
Thank you for the talk. I was wondering about this
approach that you want to do like an arrow tomographic beaming,
Yes.
how would you deal with the increasing of 3 parameters in analysis? Because in the previous talk, Ernest mentioned that if you have more tomographic beams, you will also have 1 parameter per beam. So I don't know if you will do like some analytic function or the systematics for range beam or.
Yeah, but compared to yeah, we will have a more like parameter there, but also compared to the weak lensing, we are like less suffer from the photo leak uncertainty. We are, so I didn't include here, but scale is not affected by the intrinsic alignment. So we won't have any like parameter from light end. So the actual, so I haven't like really calculating how many like parameter I'm going to have in a 30 tomography beam, like in total, whether light would affect our result. But I would say light will be much lesser than what you would expect it from traditional weak lensing. Yeah.
We have time for one more question.
Yeah.
I'm sorry, maybe I didn't see that it was on the slide, but it's a very interesting concept. Why do the spectral look different if it's, basically like the spectral. Yep.
Yeah, so this is the case for like 2 disk galaxies. So this galaxy, they have their their disk rotation have a rotational velocity, right? So on the top is a face-on galaxy. So you won't measure any like line of sight velocity in addition to the galaxy's spot motion towards. So yeah, so in the bottom, the disk is slightly inclined towards. So you will measure the rotation from that galaxies. So that's how like you can kind of break the degeneracy.
Thank you.
Let's thank you. Our next speaker is Eduardo Rosso from University of Arizona. Let's see. No. Check on that.
You'll give me like a 3-minute warning or something?
Sorry?
Will you give me a 3-minute warning?
Yeah.
Okay, great. Oh, wait, it's advancing automatically. I think. There you go. Okay. Hi, everyone. So this is, in fact, a talk about field-based inference. And what I want to do is I want to start by showing you why you should care about field-based inference. Okay, so I don't want to tell you, I want to show you what's going on. This is the mass map that the Dark Energy Survey Collaboration released using their year 3 data. So you take all the shear data from the DSY3 and you analyze it and create a map of the dark matter distribution of the universe. And this is what happens when you use the exact same data, but you model it using field-based inference. So hopefully, if I just flick back and forth a couple times, you can see that if you kind of use the traditional approach, you don't do as good of a job at resolving all of the rich structure that is in that data set. So you are able to extract way more information from data by using field-based inference than you can using traditional methods. So this is why you should care about field-based inference. So what is field-based inference? So the idea is that you start with a parametric algorithm that allows you to generate synthetic maps of the universe. So let's just use a simple example. Let's pretend the universe is just a Gaussian random field. So if I have some parameters that tell you what the power spectrum looks like, then you can start randomly drawing the Fourier modes of your universe and generate maps of what that random Gaussian field looks like. And then you can go and say, okay, well, here's my data. And so you generate a random universe and go like, does this look like the data? No, so you throw it away. Does this look like the data? No, so you throw it away. Does this look like the data? Yes, okay, so I'm gonna keep that one, right? And so that way you start generating a posterior distribution of all of the maps and cosmological parameters that are consistent with your data, right? And so if you're working at the map level, you have to be including, you have to be extracting all of the information that is available in that data set, because any summary statistic that you want is some sort of transformation on that map, right? This sounds insane. The first time I heard this, I was like, yeah, that's never going to work. That sounds way too hard. But it turns out that there are people that are very smart that have figured out how to make this work. And so I just use what they've done, right? And so this is numerically demanding, but it is actually totally doable, right? And so why bother? So one of the things that I started with, right, is field-based inference allows you to extract more information from the data. And so why is that, right? The reason that's happening is that if you did have a universe that had a Gaussian random field, right, that was just describable as a Gaussian random field, right, then the power spectrum would already contain all of the information that is available for you to extract from that map. You don't need anything beyond the power spectrum. But of course, when you're doing things like galaxy clustering or weak lensing or anything like that, the field that you're looking at is in fact strongly non-Gaussian, right? And so that means that if you're relying on two-point analyses, you're leaving a lot of information on the table. So if you can extract that additional information, if you can latch onto those non-Gaussian signatures, then you're going to be able to improve your dark energy constraints. So this is what I'm showing you here. So on the x-axis is just the amplitude of the power spectrum. On the y-axis is W. This forecast was done before DESI, so we just had W, not W naught and WA. And what you're seeing here are the posteriors that you get using kind of a standard two-point cosmic shear analysis. So that's what you get on the blue. And on the red is a forecast for what you get when you use field-based inference using the exact same data set. So we use the exact same data set, we analyze it using only the two-point function or using field-based inference, and that's the difference that we got, right? So again, field-based inference allows you to extract more information from the data that you have. One of the nice things about this kind of approach is that you can also extend it to do multi-probe, right? So one of the great things that we can do right now is do 3x2 point analysis, right? So we want to be able to do multi-probe analysis. You can also do this with field-based inference, but what you really need to do then is you need to figure out what the bias model is, and this is not trivial. But fortunately, what we can do is we can go to simulations and just look and see what happens in simulations. So if I give you a map of the matter density field and you compare it to a map of the galaxy density field, what is the probabilistic relation between those two things, right? And so that's the bias model. That's the next ingredient that you're going to need in order to be able to forward model the galaxy density of the universe, right? So the good news is we can use numerical simulations to inform us on what that bias relation is. The bad news is that the model is complicated, and this relation does not look particularly simple. So, you know, I think for those of us who kind of grew up doing cosmology, right, you write delta G is equal to times delta M and call it a day and move on, right? But if you just go to numerical simulations, that's just not what the relation between galaxies and the dark matter look like. And so what I'm showing you here is if you go to a numerical simulation, so this in this case, it's the Bolshoi simulations, the galaxies come from universe machine data. And on the x-axis is the density contrast of the matter density field. And then the y-axis is the density contrast of the galaxy density field. So matter on the x-axis, galaxy on the y-axis. And there is kind of a linear relation that goes between those points. So every single point is you just go to a single pixel in the simulation and say, what's the density contrast here in the matter? What's the density contrast in the galaxies? And you put that point over in that plane, right? And there is kind of a linear relation. If you look at it very carefully, you can see that there's really not linear. There's no part of this plot in which it's linear, but you also get very large deviations from linearity once you start going into the voids region, right? And so the linear bias models, you just can't do this with linear bias models. You can also see there's a lot of scatter, so you need a model that is nonlinear and it's stochastic. And in fact, we also know that it needs to be non-local. So the galaxy density field at this point doesn't just depend on the density contrasting matter at this point. You also need to know what the density contrast is at neighboring points. And so all of that needs to go into your biasing model. And so that's one of the things that we're spending a lot of time now working on is what does this density bias model have to look like? The other key challenge is that forward modeling must be fast and accurate to ensure robust inference. So this is very much related to what we were just talking about. We need to know the model, right? And that always has some sort of shortcut in order to make this computational feasible. So I go for the easiest possible route, right? And I think there's a lot of complementarity between these different approaches. So in the approach that we've been doing, which is Karma, what we've done is we've implemented the log normal model on the sphere. This has the big advantage that we can work natively on the sphere, and so we can actually analyze large survey areas, right? But because you're using the log normal model, you can't model nonlinearities very well, and so that does limit the resolution to modestly nonlinear scale. So somewhere between 6 and 13 arc minutes, right? But I would argue that it's still pretty awesome, and that the proof is those two plots that I showed you at the beginning of the talk. Karma is only one of many FBI codes, of many field-based inference codes. But that challenge that I just talked about of modeling the density field correctly, it really remains. So the Borg team relies on Lagrangian perturbation theory. There's this called either MICO or MICO, I'm not sure how it's pronounced, that uses AI augmented PM simulations. And so there's different approaches to do this, but at some level, this idea that you have to have the right model impacts all of them at some level or another, right? One of the things that I think is kind of fun that you can do is you can try to improve your model by using machine learning methods. And so this is just one possible example. There's a whole literature on doing this kind of thing. So this is from our own work where we use GANSky. So the idea is to train a convolutional neural network to perturb log normal maps so that they look like simulation quality maps. And the nice thing about this kind of idea is that the log normal map kind of gets you 95% of the way there. And then you're only using the AI to like just fine tune that bit. And you can put a lot of physics into what that fine tuning looks like, right? So in our case, if you don't get the mass distribution right, well, it's because, it's not because I had to grab mass from over here and put it over there, right? You just kind of had to make the peaks peakier and the voids voidier, right? And so that's the kind of thing that a neural network is really good for, right? And so you can have very small networks that are very, very stable and do a really great job. You can do things like demand rotational equivariance and so forth. And so you can do this in a way that I think is very well behaved and very promising. And so that's what the difference looks like. On the top here is the log normal map. The output of the neural network is on the bottom. The last thing that I want to point out is that field-based inference can be used to automatically detect and marginalize over unknown systematics that you have no idea they were even there in the data, right? And the reason for that is that what you can do is you can try to analyze two different surveys at the same time. And so if there are systematics affecting this survey, those systematics tend to not be correlated with systematics affecting this survey. But the cosmological density fluctuations are correlated across those two surveys. And so this breaks the degeneracy between survey systematics and cosmologically sourced systematics, right? And I want to show you I just want to show you an example of this type of work in action. So this is not actually my work. This is work by Eric Hoff and collaborators. And so what I'm showing you here is a map of what the systematic density fluctuations look like in the DESI imaging, recovered using this kind of field-based inference analysis. Okay? Oops. This is a plot of the dust map. That plot on the right didn't know anything about dust. All that was given to that plot on the right was the galaxy catalog from WISE and the galaxy catalog from decals, right? And just by looking at how those two things were correlated, you are able to reproduce that map on the right that looks basically exactly like the dust map, right? So you really can extract the systematics even if you didn't know they were there, right? So let me just end here. FBI has a lot to add to Rubin. Field-based inference can extract all of the cosmological information that is in your data. It can automatically marginalize over unknown systematics. Even if you don't know they're there, this has the potential to get things right. And fast and accurate forward modelings are definitely a challenge, but they can benefit from physics-informed neural networks, artificial intelligence, machine learning type of stuff. So thank you very much.
That was a great talk. I was just curious, you showed us karma and like the maps that are being generated randomly, and then we accept some small portion of those, and it's only feasible now because we can do a lot of compute. Can you just give me roughly ballpark, like how many maps are generated and what acceptance rate we're looking at, just so we have an idea?
Oh boy. So the acceptance rate, I think, is something like 50% HMC. So this is why I'm saying that there's people are very clever. And so HMC codes have an acceptance rate. A good HMC code will have an acceptance rate of about 50%. And so we use nuts, which is kind of the standard in the field. What we have found, and what I'm about to say will probably sound surprising, but we're not the only group that has found this. One of the interesting things about this field-based inference is that all the posteriors and cosmological parameters tend to be converged after about 100 samples or so. They tend to converge very, very, very quickly. And so we can run this kind of analysis in about 24 hours, 24 to 48 hours, depending on the details.
Thank you.
Wow, I said
yeah, so field-based inference, at least all the analyses that I've seen are about sort of recovering the field at a particular snapshot of time. But constraining, for example, models of the low and dark energy requires constraining cosmology in multiple different redshifts to capture that evolution of dark energy. And capturing the field can't just be anything from one redshift to the next, right? There's deterministic physics, which strongly constrains the allowable field. What prospects are there for extending field-based inference methods to capture redshift evolution?
Yeah, so the stuff that I showed you already captures redshift evolution. This is actually part of what I do with the normal model, because it's much easier to do this kind of thing straightforwardly. And so in the forward model, you're modeling actually just the two density fields, but you put into the model all of the cross correlation in the theory, and so you're really capturing redshift evolution as well. But there's also work, so from the simulations point of view, people have moved on to, so like the Miko work, they run this BMW simulations, and they generate light winds on the fly and do the ray tracing on the fly and get the full evolution on the fly as you're running the simulations. So it's very much, so it's much harder to do in simulations, but it does have to be work in progress. The Miko people have already managed to do this. The challenge there is that it still gets to be limited to relatively small maximum size with this the flat sky approximation. And so if you want to do this for large surveys, then that becomes harder, which is again why we did the thing. So there's trade-offs between the two, but it's very much something that everybody's going to like. You are 100% correct. You need to get this right. You need to get the right evolution.
Please follow up with Eduardo on coffee, and let's thank him again. Johannes Lange from the American University.
I think you need to go to full screen, otherwise it just automatically goes to next.
Yeah, there you go.
Yeah. Hopefully this works. Okay. All right. So Eduardo just told you about the importance of field-based inference, which is a way to study higher order clustering. And now I'm going to tell you about why you should care about studying nonlinear clustering, so clustering on very small scales. I'm going to tell you about some of the recent results we got out of the DESI survey. and I'll talk about some of the outstanding challenges that we try to address as we move towards Roman. Before really getting started, I want to highlight my collaborators, some of which are in the audience here, and particularly want to highlight the first 4 names on the list, which are undergraduate students who work with me on some of the work that I'm going to present to you today. Also, before really getting started, I want to just mention, especially in this day and age, the importance of federal funding. I'm going to present DESI results, and DESI is in large part funded by DOE, but also NSF and other foundations. All right, so if you wanted me to convince you of the importance of nonlinear clustering, I could make this case for any survey, but I think the case particularly strong for Roman. And that is because Roman, compared to other surveys, has a very, very high sampling density. And that brings with it a number of advantages, particularly for studying nonlinear scales. The first very obvious one is that by having a very high sampling density, you increase signal to noise on nonlinear scales in particular, which are still short noise limited. On the other hand, larger scales are typically already cosmic variance limited and don't profit as much from the high sampling density that Roman offers. Then, also by having this high sample density, you can also split your sample in different subsamples, let's say red and blue galaxies, and check whether you get consistent results on cosmology or gravity despite having different galaxy samples. And finally, having such a high sample density and a wide range of different galaxies over a large redshift range allows us to study in detail the galaxy connection and how baryons affect the matter distribution, which is critical for understanding nonlinear scales. So talking just a bit more about nonlinear scales, Andrew already mentioned that there are a number of challenges that come with studying the nonlinear regime. And these are 3 different ones. The first one is that at some point you just need to run simulations to really make accurate predictions for the clustering and matter distribution on these highly nonlinear scales. But then also, you need to worry in detail about what is the relationship between the galaxies that we see and the underlying matter field, or more precisely, the so-called galaxy halo connection. And finally, we also need to worry about how baryons affect the matter distribution, which is another thing that we don't fully understand yet, which is very complicated. And so studying nonlinear scales is very challenging, but at the same time, in recent years, we've made lots of progress and shown that if we're able to do so, we also get, just like with the FBI, much more stringent constraints on cosmological parameters and gravity from the same data. So it's definitely worth it. Before talking about some of the outstanding challenges, I just want to show you some of the recent results to show that this really works. So a lot of teams have made a lot of progress with this kind of analysis. There are various ways we can do this right now. Just as an example, I'm going to show you the recent results from DESI that are going to be published soon. So we analyzed the clustering of galaxies in DESI, particularly the Bright Galaxy Survey and the Luminous White Galaxies. And we modeled this simultaneously with galaxy-galaxy lensing around the same galaxies as measured by HSC kits, or DS. The top row are the clustering measurement, the bottom row are lensing measurements, and different columns or colors are different DESI samples. And don't overanalyze this. This is blind data, so there's no final cosmology result I'm going to present today, but you can see what the constraining power is. You can see through these different measurements, you can see a solid line. It's the best fit model for a given cosmology, which fits all these measurements reasonably well. And so when we do all this, these are the kind of cosmological constraints that we get on the right-hand side. Again, they're blinded, so this is not the final cosmology result, but it gives you some idea what the constraining power is. So just from this DESI year 1 data, cross-correlate in this case with actually only the HSC data, we already expect a roughly 2% constraint on S8, which is very stringent and one of the most strongest constraint that we have on this parameter for cosmic structure growth. Going back to some earlier results on SDSS, which you can see on the left-hand side, again, constraints here on S8. Our results here are shown by these stars, where we study galaxy-galaxy lensing as well as retrospace clustering. And the point is just that A, our results are very consistent with other probes, which gives some indication that the results are reliable, and also that we have very stringent constraints despite only studying actually a very small data set in that work. And so I think all this is convincing enough to show that this is something that works. And again, a lot of groups have made progress, and we can now do this kind of analysis frequently and quickly. And so it's something that we should definitely also do with Roman. Now, One the open question, of course, the elephant in the room, is how reliable are those results? Now, Andrew already mentioned that entering the precision cosmology era, we are really systematics limited, and that's especially true for studying nonlinear scales. Because you need to have some kind of model, some kind of way to marginalize over galaxy physics. And galaxy physics are messy, we don't fully understand it. And it doesn't matter what kind of model you come up with, whether it's one of those more empirical models, like halo occupation models or hydrodynamical simulations, these are the more physical models. No matter what you choose, no matter what parameters you choose, the real universe will not fit exactly into that kind of space. So some kind of model misspecification is basically unavoidable. And also, it is really hard, especially for those nonlinear scales, to rigorously quantify what the theory errors are. Like for example, for EFT, you can just add more and more bias factors, and thereby figure things out. It's much harder for nonlinear modeling. So the way forward is, just like for anything else, testing these analysis methods with mock catalogs, with detailed mock catalogs. Now, most of these analysis methods use halo occupation models or sample abundance matching to compare against observations. So the mocks that we want to test against have to be fairly complex. So we rather want to have models in this part of the diagram. So one result we got recently as part of the DESI emulator mock challenge, where we used the DIFF-SKY model together with the Gauss sampler technique applied to the unit sims. So we have a pretty large volume that we can then analyze, like re-observations, and see whether we can get unbiased constraint. So this was work led by my student, Alex Weltz, who analyzed clustering down to 1 megaparsec and lensing down to 2.5 megaparsec. And you can see the results here. And this is the input cosmology. So all this looks pretty good. There's no indication of a bias in cosmology. So it's just one of many efforts that are going on right now. I also, again, want to highlight the work by the Beyond 2-Point collaboration, who've done similar, even blinded mock tests, and also recent work, for example, by Zhongzhu Zhai, comparing the mock results against semalytic models. Now, one of the things that's still missing is tests with hydrodynamical simulations, which are the most complex simulations, which have the least intrinsic assumptions. That's, I think, one of the outstanding things we want to do. The problem with hydrodynamical simulations is that state-of-the-art high-resolution simulations like Illustris or Eagle, let's say, that are publicly available, are typically much, much smaller than the volumes that we're studying in observations like in DESI, Rubin, or Rubin. And so recently we developed a method that addresses this problem to some extent. So the way we do this is, first of all, like many people have already talked about, right? You can use AI. So you can use AI to, or machine learning, to study the relationship between galaxies and dark matter halos. You can basically feed in data from a simulation like TNG to learn this relationship and predict how many galaxies you expect in every halo. And then you can apply this to a dark matter only simulation to make predictions. And you can see on the right-hand side, this works reasonably well. It looks pretty close to the real thing, right? So the blue points are the galaxies in the full physics simulation. The red ones are the ones just on a gravity simulation with machine learning. We could use that as our model to make mock catalogs, but it would not be exactly the same thing as hydrodynamical simulation. So you can go one step further by using a statistical technique called control variates to use this model, this machine learning model, basically to apply a cosmic variance correction to your predictions from a hydro simulation, and thereby decrease the noise in the predictions. So you basically come up with a new estimator for the clustering 2-point correlation functions that basically studies how this volume in the hydrosim compares to the cosmic average, and then correct for that. So you get a new estimator with a lower variance, with a lower scatter, which is basically the same as having a larger simulation. And so in our recent work, we showed that one can do this and get an estimator that has a significantly reduced variance, such that it behaves as if the volume of that simulation was a factor of 10 to 100 times higher. You can see this here, right? So for different galaxy samples, how much the variance is reduced. If it's reduced by a factor of 10, that a factor of 10, it basically means the simulation behaves as if it was 10 times larger. And so with this kind of technique, and also current next generation simulations, like for example Flamingo and Millennium TNG that are significantly larger, we can then make mock predictions that behave as if they came from simulations that are several gigaparsec cubed in volume. And so with this kind of technique, we're currently analyzing Flamingo, making predictions, and then analyzing them with methods for nonlinear scales to see whether we can get unbiased cosmological constraints. And so there's a lot of work going on in studying nonlinear scales and testing those results with mock tests. And so hopefully, if all these are successful, we'll hopefully have confidence also applying those techniques to Roman. Thanks.
Questions? For your machine learning method of placing galaxies into halos, what properties do you require?
This is a great question, right? So yeah, what you're putting in is basically a list of halos, and what you want to fit to is just how many galaxies are there, more or less. You can split them by center of the satellites, but that's a small detail. You are free to choose what halo properties you want to use. In principle, using more will always result in a better prediction. And we do see that if you go beyond just halo mass, you also include concentration or environment, predictions become better. You have a lower scatter. You also are better in reproducing the clustering overall. Now, for this particular method, the control variance method, it actually doesn't quite matter how accurate you are. It's the scatter that matters, and that actually isn't affected very much by how many halo properties you use. So halo mass alone is already quite good for this kind of approach, which you don't even need like some advanced machine learning method. You can just use some very simple one. But yeah, it's in the paper we study like how different halo properties affect the predictions. Mm-hmm.
Any other questions for Johannes? Agnes.
Yeah, on your slides for DESI plus TS, HSC, sorry, it's a basic question, but say blinded, like, so we shouldn't look at, because you're basically showing attention to CMB, it's
sorry.
In which way? Yeah, that's my question.
So these are blinded. In S8 and omega matter, those are just not to be interpreted cosmologically. These are published results on SDSS. Those are not blinded. So there is some tension with CMB at the level of around 2 sigma, pretty much in line with other cosmic shear results. Yet all this is unblinded. This is for older SDSS results that we published 1.5 or 2 years ago.
Next thing, Johannes again. Here is Chumhato. You can share your screen and.
Sorry, I think I need to reopen. 2 minutes.
Oh.
I'm sorry. Can you hear me? Sorry.
You don't connect through the computer on this. He should just share from his screen.
Yeah. Can you hear me now?
Yes.
Yes, we can hear you and see your screen.
And my screen is on. Okay, cool. Sorry, sorry about technical issue. I think it just asked me, keep me out of the meeting, and yeah. So hi everyone. So I'm sorry I cannot be there in person. Today I'm happy to share our latest cosmological constraints from joint analysis of cluster galaxies and weak lensing. So I'm Joe. I'm a postdoc at the University of Chicago. Sorry, there is some noise in the meeting room, but I'll probably just ignore that. Okay, so first, I want to do this talk a little bit differently. So instead of showing you details about one specific analysis, I would like to zoom out a little bit more to show you the range of science one can do with these combinations. And I'll talk about some of the future implications of the Roman survey. So first, I want to show you the beautiful image took by the Dark Energy Survey. So here you can see a beautiful galaxy clusters on the sky. And if we zoom in a little bit, we can see a beautiful distorted galaxy shape due to the gravitational potential of the galaxy clusters. This is an effect known as the gravitational lensing. In most of the cases, this effect is very tiny. But we can measure them statistically by using lots of galaxies, like a survey like Rubin. So we can extract this signal. But if we zoom out again, then we can see there are lots of galaxies that live outside of the galaxy clusters. So this image is quite complicated for cosmologists like me. So I make this carbon picture. So we have, we all know that for a large survey like DES and Rubin, there will be rich sets of observables. And I just described we will have galaxy clusters on the sky. We will have galaxies that trace the same large scale structure. But we also have the galaxies living in the background whose shape is going to be coherently distorted by the same large scale structure. So we have these three different probes, galaxy clusters, galaxies, and weak lensing. They all trace the same large scale structure. I'm interested in thinking about, can we use all observables, all these three observables to piece together the structure formation history of our universe. So I'll review a little bit of our efforts so far, and all of the stuff I showed here has been already applied to stage 3 data. So as I mentioned before, we have galaxy clusters, galaxies, and weak lensing. We can first consider the cluster-related two-point correlation functions, so including the cluster-galaxy correlation, cluster-weak lensing correlation known as the cluster lensing, and also the cluster autocorrelation, the cluster clustering. But if you combine those data vectors together, then you will get the constraints shown as the blue contour. And this is the result from the DESI data set. So the y-axis here is the SA, which is the amount of structure in our universe, and the x-axis is the amount of matter in our universe. You can do a little bit differently by combining the galaxies and weak lensing and their cross correlations, and I hope Anjas already covered this part. But this is known as the 3x2 point analysis, and their constraint is shown as the green contour. But you can also combine all of them together, and by combine, I really mean that we perform a joint analysis of clusters, galaxies, and weak lensing all together. And you really need to do that because different data vectors are not completely independent. So you really need a theory framework to really quantify the redundant information, so you wouldn't double counting the information. But also you need a theory framework to describe the shared systematic. So you need a unified model for all these different probes together. But if you do all of that, then you will get the constraints that show as the orange contour, which is tighter than each of the individual probes. In the Dark Energy survey, so this is the result from the ES3 data, and right now we are actively working on analyzing our full data set. So later this year, we are expecting to get improvements on our constraints. So this is some of the forecasts that we run. But we not only do on the lambda CDM model as we did in DES ES3, we are also actively working on to get the constraints on the evolving Dark Energy equation of states. So because the degeneracy between the Dark equation of state and omega matter is quite different between the galaxy clusters and 3x2 point analysis, and between clusters plus 3x2 point analysis and the type 1a supernova. So if you combine these probes together, we are expecting to get quite competitive constraints on the Dark equation of state. Okay, another exercise one can do is one can just replace the galaxy clusters that we found in the dark energy survey by the galaxy clusters found in other wavelengths. In this case, we use the galaxy clusters from the CMB surveys or from the South Pole Telescope. So this work is done in collaboration with Sebastian Phuket. And here you can see that the cluster constraint is shown as the blue contour, and the usual known 3x2 point analysis is shown as the green contour. But if you combine the clusters and 3x2 point, because the degeneracy direction is quite different, so you are expecting to so basically we get a very huge improvement in cosmological constraint. So this all looks great, and I just show you two examples on the data that we can extract cosmological information from combining clusters density and galaxy clustering. I show you two examples. One use the DS clusters and the other one use the SPD clusters. And in both cases, we see a huge improvement in the cosmological constraint. So 2 years ago, I've been thinking about can we really do more than extracting cosmological signal? So let me zoom in a little bit on this part of the data vector, which is weak density, or specifically the autocorrelation of the weak density known as the cosmic shear. And on your left-hand side is the data. So the dot with the arrow bar is our data from the Dark Energy Survey year 3 result. The key point I want to make is that all the data in the gray region are removed in our analysis. And the reason is because we don't know how to really model the baryonic physics, and this constitutes about like 1/3 of the signal to noise that we removed for our analysis. But for galaxy clusters, we actually do have some knowledge about the baryons, while most of the stuff in galaxy clusters is in the form of dark matter halo. But around 10% of the mass is in hot gas, and that makes them shine in the X-ray and millimeter sky. So here I focus on the millimeter sky, where the signal comes from the thermal Salyut-Leodolbeck effect. And the idea is that when the CMB photon go past the hot gas of galaxy clusters, they are going to be inverse Compton scattered. So they leave an imprint on the CMB map. So you can find those little shadow in the CMB map to find the galaxy clusters. So I start to do a case studies by leveraging the great overlap between the South Pole Telescope and DES. So the dot, each dot here is the beautiful galaxy clusters found in the South Pole Telescope, and the background image is the weak density mass map from the DES. So the idea is that whether we can use the AZ effect to measure the baryons, and whether those information is going to help us for the weak density analysis. So I start from doing some analysis on the hydro simulations. So here I use the magnetic simulations. So the y-axis here is the min max, which is roughly what you can measure from the cluster density. So the cross correlation of galaxy clusters and weak density. And the x-axis is the TSUY or the 3D TSUY signal. This is not observable, but later we'll talk about how we translate this information into some observable. But we can measure this in a simulation. So the dot with the arrow bar is what we measured in the magnetic simulations, and we can create a model. And here we use a halo model that have some baryonic components to fit this measurement in the simulation. So the result is shown as the blue line. But once we fit the model, we can use that model to make a predictions, right? So to understand what's the impact of baryonic physics on the matter clustering. And this is the key theory uncertainties in the cosmic shear analysis. So the result from the model is shown as the blue dot with the arrow bar. So if this curve is less than 1, means that there is less mass clustering due to baryonic physics compared to the gravity only predictions. And because we do this in the simulations, so we can really to understand what's the true answer, which is shown as the green line, right? So you can see the comparison it looks actually pretty good. We can really recover what they should should be in the hydro simulations. But now you might ask, okay, so I validate this approach, use one single hydro simulations. Maybe my model is overfitting into less specific hydro simulations. So in this paper, we also do it in another simulation, which is electricity and G300, that have a much weaker feedback. And therefore, the min mass of the clusters given Y signal is slightly lower, as you can see in the plot here. But in that case, we repeat the same exercise, and we can still recover the suppressions of meta clustering. In the interest of time, because some technical difficulty, I'll probably skip the implication of the cosmology constraints. But here I want to really show you that all the stuff I showed before is basically some theory calculations. But recently, Nihal Dalla, who is actually in the conference, applied this idea on the egg TSZ selected clusters with DES weak lensing. So what we get is the left-hand side is the min mass given Y, which we get from the DES weak lensing, and the x-axis is YSZ that we can measure in the egg map. So the white dot with the arrow bar is our measurement. Different line is the model. And once you fit the model, then you can use the model to make up predictions on the change of matter power spectrum due to baryonic physics, and compare that with the different hydro simulations. So our constraint is shown as the blue line with the arrow bar showing you 1 sigma and 2 sigma arrow, and different color line correspond to a different hydro simulations. So here you can see that our preferred feedback strength is actually stronger than most of the hydro simulations. So for all the details, please go talk to Nihal Dalla, who also have the posters in the conference for more details. But finally, I want to talk a little bit about Rubin. So so here is the blueprint of the recommended high-energy wide area survey. So the white region and the median region. And I overplot that with the ongoing SPT 3G survey. So there are basically 3-tier survey. The yellow one is the SPT main survey, which has the best noise. And for the blue one and the red one have roughly 4 times and 6 times worse noise, and that's basically overlap with Rubin. But the overlap of Rubin with the SPD3G main survey is actually pretty low. So I think maybe we can have some geo program to a southern part of the sky. They might help. But I'm happy to talk with people in the conference. Okay, so here's the conclusions. So I show you 2 examples on the analysis on the real data. On the joint analysis of galaxy clusters and weak lensing and galaxy clustering. One use the DES clusters and one use SPT clusters, and in both cases we see a huge improvement on cosmological constraints. And these combinations can also be used to constrain baryonic feedbacks to a level that's actually good, very good to recover the removed signal to noise in the cosmic shear analysis. And Nihal Dalla recently applied this on the real data using egg clusters and DES lensing. And what he found is that the impact of baryonic physics is stronger than most of the hydro simulations. So later, the overlapping between the Rubin and the SPD survey is actually not great right now. So I hope maybe there's some other programs can actually help to improve this overlap. Thank you.
Thank you. There is time for one question. Yes.
Hi, Chunhao. I really appreciate your very nice work. I'm just wondering if the biophysics of the cosmic shear and the galaxy cluster is modeled in a self-consistent way. If that's the case, like based on the current constraint from DES and cluster survey, can you constrain the bion physics simultaneously with the cosmological parameter? How was the constraint? Is the parameter, like, I know there are usually many parameters describe the gas profile. Can those parameters can be constrained in future survey, in your perspective?
It's a very good question. This is actually on the side that I ignored. So the answer is yes. I think with everything that we have right now, the hope is actually do a joint analysis of clusters and weak dancing together to fit the both cosmological parameter and all the baryon physics parameters simultaneously. And that's actually some of ongoing work that we're doing right now, actually with the SPT and DES. But there are like a lot of how do I say, a lot of infrastructure that need to be done. And I think we do have developing quite a bit of infrastructure already. I think we should be expecting to get some of the results like in maybe 1 or 2 years.
Let's thank Chuha again. Coffee served, and we'll be back at 4. Thank you. Also, feel free to check out the posters.
The field level inference systematically different. I haven't heard, not necessarily a whisper, specification of the galaxies. Yeah, no. Not theory systematics. So observational. So ideally, run field of inference.